In this video we'll show machine learning implementations on different datasets using Python. Problem formulation electricity dataset. This is classification problem of electrical grid stability into two classes, 1. Stable, 2. Unstable. Olivetti dataset recognizing face with highest accuracy using machine learning algorithms, comparison of their accuracies to select the most fitted face recognition algorithm. About electricity dataset, electrical grid dataset in which we have different attributes for examine the stability of the system. We will examine the response of the system stability depends on 10,000 observations and 13 attributes. One class is attribute, stab. Attributes are given in dataset as tau, x, reaction time of participant, real from the range, 0.510 s. P, x, nominal power consumed, negative, / produced, positive, real. G, x, coefficient, gamma, proportional to price elasticity, real from the range, 0.051 s-1. Stab, the maximal real part of the characteristic equation root. If positive, the system is linearly unstable, real. Stab, the stability label of the system, stable/unstable. Head of the data set. The head of the dataset is useful for quickly understanding what kind of data you are dealing with, especially when loading or exploring new datasets. Preprocessing is a crucial step in any machine learning pipeline, involving the transformation and preparation of raw data into a format suitable for model training. Proper preprocessing ensures that the data is clean, consistent, and in the right form to improve the performance of machine learning models. Below are some common preprocessing steps. 1. Handling missing data. Imputation. Replace missing values with statistical measures like the mean, median, or mode, or use more advanced techniques like k-nearest neighbors, KNN. Imputation. Removal. If a feature or row has too many missing values, it might be best to remove it entirely. 2. Feature scaling. Normalization scales all the features to be within a specific range, often between 0 and 1. This is useful for algorithms that require distance calculations, like KNN. Standardization centers the data around the mean with a unit standard deviation. This is particularly useful for algorithms like support vector machines, SVM, or logistic regression. 3. Encoding categorical variables. Label encoding converts categorical labels into numeric values. For example, cat, dog, and mouse might be converted to 0, 1, and 2. One-hot encoding converts categorical variables into a binary matrix. Each category is represented as a binary vector, e.g. if there are 3 categories, they would be encoded as 1, 0, 0, 0, 1, 0, and 0, 0, 1. 4. Dealing with imbalanced data. Oversampling increases the number of minority class samples, often using techniques like SMOT, synthetic minority oversampling technique. Undersampling reduces the number of majority class samples to balance the classes. Class weights assigns more weight to the minority class during model training to make the model pay more attention to it. 5. Dimensionality reduction. PCA, principal component analysis, reduces the number of features by transforming them into a set of linearly uncorrelated components. Feature selection selects a subset of relevant features based on statistical tests or model-based importance. 6. Data augmentation. For image data, techniques like rotation, flipping, zooming, or cropping can create new samples from existing ones. For text data, synonym replacement, back translation, or noise injection can create variations of text data. 7. Outlier detection and removal. Z-score removes data points that lie beyond a certain number of standard deviations from the mean. IQR, interquartile range, identifies and removes outliers that lie beyond the acceptable range based on the first and third quartiles. 8. Feature engineering. Transformation, applying mathematical functions like log, square root, or polynomial transformations to features. Interaction features creating new features by combining existing ones, such as multiplying or adding two features together. 9. Text data preprocessing. Tokenization splits text into words or sentences. Stop word removal removes common words that do not contribute much to the meaning, e.g. the, is, and. Stemming/lemmatization reduces words to their root form, e.g. running-run. 10. Splitting the dataset. Train test split divides the dataset into training and testing sets to evaluate the model's performance. Cross-validation splits the data into several folds and trains the model on different combinations to ensure robust performance. Head of the dataset. Principal component analysis, PCA, is a widely used dimensionality reduction technique in machine learning. It transforms the data into a new coordinate system, where the greatest variance by any projection of the data comes to lie on the first coordinate, called the first principal component, the second greatest variance on the second coordinate, and so on. Key concepts: dimensionality reduction. PCA reduces the number of features in a dataset while retaining as much variance as possible. This is particularly useful in reducing the complexity of data without losing important information. Principal components: these are the directions in the feature space along which the data varies the most. The first principal component accounts for the most variance, and each subsequent component accounts for as much of the remaining variance as possible. Orthogonality: principal components are orthogonal, i.e., they are uncorrelated to each other, ensuring that each component captures unique information about the data. Eigenvalues and eigenvectors. PCA involves calculating the eigenvalues and eigenvectors of the covariance matrix of the data. Eigenvectors determine the direction of the principal components, while eigenvalues determine their magnitude, i.e. the amount of variance they capture. Steps in PCA: standardize the data. This ensures that each feature contributes equally to the analysis. Compute the covariance matrix. This matrix expresses the covariance, i.e. the degree to which two variables change together, between pairs of features in the dataset. Calculate eigenvectors and eigenvalues. These help identify the principal components. Sort eigenvectors. Eigenvectors are sorted in descending order based on their corresponding eigenvalues, with the first few forming the basis for the reduced feature space. Transform the data. The original data is projected onto the new feature space defined by the selected principal components. Classification using PCA method 90:1080:2075:2570:30 confusion matrix naive Bayes 0.7060.6985.0.6932.0.6997 KNN, n equals 12. 0.6860.6735.0.6660.6723 SVM, 0.6940.6890.6848 decision tree 0.6180.622.0.6352 0.6216 random forest 0.6610.661 Classification using without PCA. Use standardization method 90:1080:2075:2570:30 confusion matrix naive Bayes 0.8310.832.0.8330.83466 KNN, n equals 12. 0.9060.9102.0.91080.909 SVM 0.810810.81080.823 decision tree 0.8790.87150.869 random forest, n underscore estimators equals 60. 0.9230.9215 0.9160.9186 Selecting different features and results naive Bayes, accuracy 0.982 knn, accuracy 0.964 decision tree accuracy 1.0 random. Forest, accuracy 1.0 SVM accuracy 99.2 test, 0.05. Best algorithm fit for electricity simulated data set for classification random forest, using n_estimators equals 60 test dataset, 90 to 10 accuracy equals 0.923 confusion matrix, although the KNN and SVM has given good accuracy at ratio of 95 to 5, but it is only on test dataset, need further evaluation on training dataset. By selecting different features, the accuracy observed is 1, but the model is overfitted, need preprocessing and proper selection of features to train the models to improve accuracy. Step 1. Load and explore the data. Step 2. Visualize the data Olivetti dataset. Python packages used. Reshaping data is a common task in data preprocessing and manipulation, particularly when preparing data for machine learning models. This involves changing the structure or dimensions of your data to match the requirements of specific algorithms or analytical tasks. Here's a guide on how to reshape data using Python, with examples using pandas and NumPy. Reshaping data with pandas. Pandas provides several methods for reshaping data, such as pivot, melt, stack, unstack, and transpose. Below are some common reshaping operations. Accuracy metrics comparison without PCA method 90:1080:2070:30 naive_Bayes 92.587.5073.33 knn 90.091.25 90.00 random forest 90.093.75 93.33 SVM 95.096.25 96.67 Logistic regression 95.097.50 97.50 Dimensionality reduction using PCA. Dimensionality reduction using PCA. Dimensionality reduction using principal component analysis, PCA, is a powerful technique to reduce the number of features in a dataset while retaining as much of the original variance as possible. This is especially useful in scenarios where you have high-dimensional data, and you want to reduce complexity, improve computational efficiency, or mitigate the risk of overfitting. Steps for dimensionality reduction using PCA. Standardize the data. PCA is affected by the scale of the data, so it's important to standardize the features so that each has a mean of 0 and a standard deviation of 1. Compute the covariance matrix. This matrix captures the variance and covariance between different features in the data. Calculate eigenvectors and eigenvalues. These determine the directions, principal components, and the magnitude of variance captured by each of those directions. Sort eigenvalues and select principal components. Sort the eigenvalues in descending order and select the top. K eigenvalues, where K is the number of principal components you wish to keep. Transform the data. Project the original data onto the selected principal components to get the reduced dimensional representation. Next example is in the part 2. Please watch.